Hi, in this video, we were assisting a customer who was using a Vacon drive from Danfoss. There was a EtherCAT card in the drive, and the question was, is it possible to run this drive just purely using the status word and control words? So instead of using our NC capability that's built into TwinCAT, they just wanted to drive it themselves. And this is the video that come from it. From what I can see of your emails, it looks like you've already done these first steps, which is a good thing. I will just run over it just to make sure everything's been caught. First thing is to install the manufacturer's XML file or ESI file. They will provide this to us, and we just drop it straight into C drive, or whatever drive you've installed TwinCAT on. TwinCAT 3.1 config IO EtherCAT. Drop it in here, restart your development environment, and it'll then find that file. So we can shut that out of the way. This project here, I've dropped in a EtherCAT master already, and that was just purely by saying add new item, EtherCAT master. Now, the EtherCAT master, when you haven't got hardware already to scan, you're just dropping an EtherCAT master in there. You're actually saying, I have an EtherCAT master. You don't need to know who it is yet. But because we're doing the hardware creation ahead of time, before I/O, when you come to deploy this to your IPC, you will have to go back into this EtherCAT master and select its adapter and actually search for the adapter you wish to assign the EtherCAT master to. So there we go. So that's, a lot of people get confused, especially when they say, I have a C6015 or a CX5130. Where is its port? Where is its EtherCAT master? It's not. We just define it straight as an EtherCAT master, and then after the fact, we then tell it which port it's using. Had you scanned the hardware in the first place and got the true EtherCAT master port, it would have already filled this information in for you. Okay. Next, we will say I'm going to add a new item, and let's just make the assumption that the only thing connecting it is your IPC and your drive. Now you can see I've already done a search for it here, but that was just a case of typing in Optech, and it's filtered my list and it's given me the available options card. So if I double click on this, it's now added it to our project. PDOs, what this drive is doing is the drive manufacturers have said, yes, it runs on EtherCAT. We make data available to you as you, the programmer, and these are the PDOs we want to cyclically give to you. Now, that's not necessarily all the information that's inside the drive. It's just the information they want to cyclically provide. There is other data in a drive, and quite typically you'll have to do some form of ADS read, ADS write to get that data from them. But cyclic data tends to be the data you need to use the drive in almost every situation. It tends to be small things like, I'd like to see what temperature the drive's running at, something along those lines. You may have to specifically put it out, or what version of firmware is the drive using. Then you have to be more specific. So what we can see here is they've kindly provided us with the first, the second, the third, the 17th of both inputs and outputs mapping. Again, it's up to the drive manufacturers of how they name this. Some people just go straight in and say, this is the control word, this is the actual velocity. But they have grouped them into just first, second, third, 17th. Now, looking through their documentation, they have mentioned that CIA 402 drive profile is used. Now, this is common amongst most drives. You'll typically find that there were so many people making drives and so many different control strategies of those drives that they actually standardized. There are some standards out there, and one of them being this 402. So this is what this drive, from my reading of the datasheet, says that by default its card is set up to provide, to receive and to provide to you. So it's working with 402. We can see that it actually gives us clues to this, because when I open up the first PDO mapping, it talks about CIA 402 status word and velocity actual. And then from the outputs, the things that if we put a value on here, it's because it's an output, we're sending it out of the IPC. We have a 402 control word and a target velocity. So this is how we poke and push the drive to make it react and do things. So far so good. We've added the hardware. The project is happy that the hardware's been added. We can somewhat ignore the rest of these PDOs, because looking through the datasheet, they speak about a bypass mode and being able to implement their own drive profile. That's not default. That's something that they themselves do, and there may be good reasons why they do this, but they've actually set up on default saying, well, actually, no, for the best of the times, use 402, and that's the first PDO messages. Right. Next step is how to run this via your IPC. So what I'm going to do, I added a PLC program just by saying add new, standard project, use empty project if you want to make a library, but anyway, I digress. With this, I'm going to show you one route first because there's many ways of doing this and it really does depend on the style of coding you like to do, but I'll show you some options that are open to you. So the first thing I'm going to do is just make a global variable list. Don't need to use global variable lists. Some people bake it into a function block or a program. But again, this is one way that I've seen people apply. So what we need to do is we need to map these variables here into something our PLC programs can then use. So I have here, we know that we have a status word. Oh, sorry, let's put that together. And I'm just going to call that drive status word. So I have a drive status word. I know it's %, %i star, which indicates that it's an input to me, and I need to give it a type. So what size is this value? So we can go down, double click on the status word, and we see that it's an unsigned integer. So if we go back up into here, make that an unsigned integer, and just to make sure we, oops, sorry, missed my code on. Okay, shortcut for build is Control-Shift-B, just so you know. Typical warning of TwinCat. If you are starting to have variables in your PLC program and you've got hardware in your hardware configuration and yet none of them are linked, it comes up to say at least one thing needs to be linked for the I/O to actually go live. So that's just a standard warning that you'll see. There's nothing to worry about with that. So we've defined a drive status word. So we'll stop at that point there and we'll just show you how to link this. So all we do is come down to this status word here. This will only appear after you've built it. So you have to compile your PLC code, which was Control-Shift-B or build solution. And now we can say link to, and it's given us the variable that we've just made up in this GVLIO. And it's saying that I'm happy to map status word with this because it's the right size. So if I OK that, and let's quickly knock out the other ones that we have. So we have drive velocity actual, which is at %i star. The star indicates I don't care what size it is. You are the compiler. You work it out yourself. So in the old days, people could actually say, I want that to be at I0, I0.2 if it's a bit. Long gone are those days. There really is no need to do this anymore. %i star means there is an address range in there somewhere. As a compiler, you manage it. I don't want to be worried about that type of thing. So that was drive velocity, velocity actual. Velocity actual is an integer. Let's just check the other ones. Control word is unsigned integer, same as the status, and target velocity is also an integer. So we can now put those in as well. So let's just put an integer here, and I'm just going to copy those out and change status to control word. We've got to reverse the direction, so control word, because it's heading out the IPC to the drive, is an output, and they call the last one target velocity. So that's target velocity. Simple as that. There we go. So we run a compile, a build, because it's only after we do a build that they show up in this assignable I/O. Actually, that was a good check because we can actually see that my target velocity is still input. So let's just change that. Save it, build it, and we'll see that that will make it jump down into outputs now, which is correct. Status, velocity actual, control word, and target velocity. So let's just assign the other ones. You can assign in both directions. So we can start with the velocity actual and link it up to the symbol. And you can see just how tidy that is. There's not many symbols in our program already. It's also ticked to say show only unused. So typically, as you're making your way through a project file assigning symbols, this list will get smaller and smaller and smaller. So it's the easy way of doing it. If I show you the other direction, so we can go from the symbol to the hardware, there's a lot more going on because we're actually hitting other symbols, other hardware that could accept that size data type. And it doesn't know what we're doing. So not the easiest. So we can, our control word, it is living there, but it's in amongst everything else. If you start getting more and more and more IO in your IO list, that list is almost going to be, it's going to be too hard to traverse. You may as well go from hardware up. Much easier. So, but we'll just prove that we can do it in that direction. And when we do, you see the two take effect. So if I go into the control word now, we can actually see this. It shows me the link I've done in the other direction. And to finish it, we'll do target velocity, and I'm going to do that. It's just the easy way. Save. Okay, we'll just make sure everything is okay. Sorry, you can't run a compile. Sorry, I hit save there just at that point where I've just renamed its control word. Absolutely magic. Let's see if that'll undo, which it won't. It shouldn't matter. Let's just put this in. That was target velocity. Okay. Just something to bear in mind when you're doing Alt F8, Control Shift B, which is quite quick. You get used to that. Right, we're good to go. So at this stage here, we now have the hardware linked with the software, but there is no software on the other end to actually do anything with it. So there's nothing in our main. And we can refer straight back to their user manual. So making our way down into the commissioning section, they say as a typical, I mean, they run you through the process that I've already done so far. They then say, right, just to give it a quick test, to run the motor, what you need to do is hit the control word with the hexadecimal value of 80. You put a target velocity in, and in this instance, they're going to put 200, which is C8 in hex. Then hit the control word with 6, which is a ready to switch on state. And then you hit the control word with F, which is operation enabled. And at that point there, the drive should start turning at 200. So that's their small example that they've done. If we were going to replicate that example, let's just see how well we can replicate that just on the fly. Do love a bit of live coding. What I'm going to do just for fun, I'm just going to drag that information just up here, just so I can read it and comment out as well. Auto commenting, I believe it lives in edit, advanced comment section, Control K, Control C. Quite handy. If you've got a multi-button mouse, you can just assign it to your buttons. I highly recommend assigning copy and paste as well to the two side buttons. You'll never go back. Right, so what we need to do now is we're going to make just a simple test program. Let's just go with this. So something along this line, we would need to do some form of state machine, I would say, because if you think every cycle of the PLC needs to issue a command, do something, issue a command after, do something. So we can't just throw all the commands straight at the commands, that word, because it will never leave the PLC program and head off onto EtherCAT. So you have to put a value in the control word and then allow the PLC to cycle. And ideal ways of dealing with this is something like a state machine. State machines, you can either use numbers to do a state machine. So we could write in here, let's say it's a drive state, and this could just be an integer, for example. And we can then do something like a case of drive state of, and then you can use magic numbers to say, well, 0, do something. Let's just pad this out. So 1, do something. Let's have a look. So we're doing step 1, step 2, step 3, step 4. There we go. So we've got 4 steps resulting in this, starting from 0. So therefore we've got 4 steps. All good. There's nothing to stop us doing state machines which have magic numbers as their state. The only downside of that is when you read that from a programming point of view, it's not easy to understand what these individual states are. A much better approach is to do inline enumeration. Now from that we could say the first word is request, and as a rule of thumb, we'll do enumerations in all capitals with underscores. We're going to do reset active false is our first one, which we can see here. I mean, they say don't write comments, just write readable code. The next one is we're setting our target velocity. So let's tell them that. Set target velocity. Okay, next step, 3 is ready to switch on. So set ready to switch on. And the final enumeration is operation enabled. So set operation enabled. Okay, so we've got a simple state machine there. The other thing we can do, we can initialize the state machine and say that whenever we start, I want you to start there. Well, actually, let's put one more state in because we don't want it to just jump straight into action when we download the program. So I'm going to make an initial state called idle. Okay, and that's where we start. Okay, let's just compile that. We don't need to, but it's always good doing a quick build just to make sure you've got any build errors. Now we can start replacing out our case, and our case will now start to read correctly. So let's just drag these ones in here to say reset active false, set target velocity, ready to switch on, and set operation enabled. So already we can now see that these are the states. This is what we're going to be doing inside them. So reset active false, we're saying make the control word equal to 80 hex. So again, we'll do some best practice in this. We should be saying GVL IO dot control word, which is, let me just turn off my caps lock. GVL control word. So we're saying control word. I'm just about to give you a value, and I want that to equal hex in backoff is 16 hash 80, I believe. So that's telling me that I'm using a hexadecimal value of 80, which is great. So jobs are good. That's our first thing done. We are also doing other control word stuff. So in Pint 3, which is setting to ready switch on state, so we can just copy that code out there, especially using your mouse if you have a mouse that can support that. That's saying give the value of 06. And lastly, we are going to do the final one, which is word 15, F at the end. So that's OF. Awesome. So that's that one there. And the final thing they're saying, at that point there, we should be making our target velocity equal to 200. They're using hexadecimal for this. In this instance, I think we should use just an integer because it's velocity. It makes sense. No one ever talks in velocity in hex. So with this one, we can say GVL IO dot target velocity is equal to 200. And I'll accept that because it's an integer. So far so good. We've just completely replicated their example code. So at that stage there, we're looking good. We don't have anyone to deal with idle yet. So I believe we've got the default state as well. No, we don't. There is definitely a default state in here. Or is it an else? Sorry, I program a lot of languages. So we do have the ability to do else, which could say just sit and wait for something, or we don't actually implement it, and then there's nothing that'll actually take effect. Let's just get rid of our comments as well, just because we don't need those anymore. So what we will do is we'll make a small trigger to start the program. So I'm going to make a boolean called start. It's starting off false. I tend to be slightly, I tend to be quite slightly explicit with things, especially if they can cause motion. I wouldn't like things just jumping into action, and it doesn't help having an end of line terminator there. Right, so start is going to start off false. I'm actually going to call it start trigger. There we go. Right, so we can just put a small if statement in here. So if start trigger it is true, because that's what I'm going to assess it to. Then drive state is equal to reset active faults. Okay, I'm not going to do any outside cases where if this thing gets stuck, if it doesn't do it, it's just going to go all the way through to set operation enable. End of example. If you want to do implement starting, stopping, everything else that you would do in a drive, I'll leave that in your domain. Hopefully this is enough to get you up and running. Another really handy reference is, which I will also send when I send this video to you. This one here, commissioning without NC, so status word and control word control. Now, this is the state machine of a 402 control strategy. So what we can see here is some of these values. So this 80, for example, 80 is in hexadecimal. If we do if we do a hexadecimal conversion, that's the first set. Sorry, just one phone wants to chat to me. This is the first set, so that would be 0, and this one here is 1, 2, 4, 8. So you can see here 8, 0 is classed as fault reset. So, and they actually say there, if you give the control word of 8, 0, you'll go from a fault state into a switch on disabled state. In order for you to get out of that and start heading up this route, these are all the different codes you can do. Now, one thing is apparent, and this is another nod to the whole some drive manufacturers don't follow the standard exactly. They're telling us to say issue a 6 to start with to put it into ready to switch on. So if we compare that back to our diagram, that's exactly right. We're going from switch on disabled. The first here is 0. The second one is 1, 2, 4, 0. So that's, 1, 2, 4, 8, and the 2 and the 4 are high, which means that's the value of 6. So exactly to their example, we're going to go from switch on disabled to ready to switch on. The funny thing is, at that point there, they're saying that we should, if we're following the right process, we should also follow it up with 7, because that's got an extra 1 at the end, which will put it to switched on. Their drive obviously doesn't care about that. That's quite happy. It will go from ready to switched on to switched on automatically. They don't care. So that's fine. So that's just another step we don't need to do. And then the last thing that they're showing us here is we issue OF. So OF, if we look at that, is enable operation. Exactly what they're telling us in the standard. If I issue 1, 2, 4, and 8, which is F in hexadecimal, so 0F, we move up into operation enable. So from this, you can now apply your entire state machine of pushing and poking your drive into making it do its thing. And the last thing, just to conclude, because I have been rambling for quite a while now, just get rid of some magic numbers. We don't like magic numbers in programming because no one knows what that means. No one. There's no point. You don't know it. We're doomed. You can either put it in here, or you can put it in the GVLs, or you can put it into somewhere else, wherever you fancy doing it. We would do something like a var constant. And we are going to start just pinching things straight off here. I think this is a picture, so unfortunately I can't do it. They class that message there as fault reset. So that's exactly what I'm going to call it. So I'm going to call it fault reset. I could prefix it with the fact we are running, its short name is DS402. So we could, just in case we've got other fault resets, I might say that's a DS402 fault reset. And I'm going to make that equal to 16. All right. And now, we've got to actually define that as what it is. This thing was an unsigned int off the top of my head. We can just double check our control word, unsigned integers, which are. So we've just now defined that as a constant, and now we can take that and replace this with this. Now that reads much better. So while the drive status is in the reset active faults, then make the control word equal fault reset. Perfect. There we go. We've done away with magic numbers. That's fine. People up here, we can assign magic numbers to constants because it's a constant. There's no other code surrounding it. People then realise that D402 fault reset is a hexadecimal value of 80. Perfect place for it. Brilliant. I won't worry about swapping the rest of them over, otherwise you're just going to watch me coding. There are ways of breaking up the control word further. The control word itself has actual meaning to each bit of the control word, although in more often than not, you're going to be working with it this way. You may as well predefine a load of your control words as constants, and then you just feed those constants in and follow this state machine. You can actually see here, if we were to apply the state machine correct, actually, that's one thing that our state machine's not going to do. I haven't actually finished anything yet. We haven't pushed it to the next state there. Let's just put those state transitions in. So drive state is now equal to set target velocity. Otherwise, it would have just got stuck on the first state. Once we've set the target, once we've done this, let's just copy and paste these. Drive state, we will just go back into the idle state once it's finished doing. Oh, no, we'll just park it there so we know it's in set operation enabled. We just need to pass in each of the next ones. So set target velocity, once we're in set target velocity, we're going to do ready to switch on. From ready to switch on, we're doing operation enabled. And just terminate each one of those lines. There we go. Otherwise, you would have a state machine there doing absolutely nothing. Now, correctly implementing the true transitional state machine, if you were going to do this something like this state machine here, they actually tell us what the status words should be coming back from the drive too. So in best practice, you wouldn't just be blindly firing control words at your drive and not worrying about its reply. What you should be doing is for kickoff, you know you're in fault when your status word equals 0. You have to mask these because the X stands for don't worry about this value. This value could be anything. It could be a 0, it could be a 1. So you have to mask those values out. You can do that by ANDing your value that you return with a mask. If I was to AND that with 0, 1, 0, 0, 1, 1, 1, 1, that would give me the perfectly formed status word back to evaluate it for fault. Okay, so you do have to do masking. Now, in this instance here, let's say we issued a ready to switch on command. They're saying that once that has been successful, they will return back x01, x0001. So we would have to mask it. So we would have to AND this with 0, 1, 1, 0, 1, 1, 1, 1, and the status word with this. And only upon receiving this would you jump from the state here to the state here. So that would actually be your state jump. Where at the moment, we're blindly firing off a control word and changing state. So if you are going to truly implement a proper state machine, you should be watching the status come back. And likewise, then when you know that you're in a running state, you should just be evaluating the status word for, has the status word gone into fault? And then therefore, that's your fault reaction. And you can propagate it from there.